Okay, I hope my screen is visible now.
Yes, sir, visible. Yes,
Okay,
sir.
done. Thank you. So we were discussing about uh, characteristics of a scientific application. So whenever you start imagining for what kind of applications I really require parallel processing or MPP, as stated in the initial content of this chapter, massive parallel processing. So just to have a fair idea, there are problem statements which really require parallel computations or n number of cores, or the multi-core or cluster computing is required, and how they are achieved or accomplished. To have a rough idea about that, this chapter gives a fair idea about some of the applications. So he has taken few applications, FFT, LU, and the two kernels, as well as what is it? Two applications. One is with respect to the prediction of evolution of galaxy, and the other one was with respect to the ocean currents. So these are the problem statements, and I feel, at least I am not having a sufficient mathematical background to deal with respect to that algorithms, whether Bernstein algorithm, what is it, whatever the applications he has taken. So that algorithms are totally I'm not aware of. But with respect to computer architecture, what I can see is there is a fairly enough scope for parallelism. So there is a scope for grid creation, and what do the real problem statements mean, and how they are implemented across can be demonstrated by them. So that is sufficient for us, and I feel with which I can continue, because again only 6 hours allotted. Whenever you look into YouTube and other available online resources, there is a lengthier or elaborative sessions on only one topic, say Bernhardt or these are algorithms, whatever Barnes and Ocean applications. Whenever you look into those simulations, there are plenty. As that is only two applications. Otherwise, yesterday we have a list of problem statements, um, where every field has its own. It's again in body problem statements. I am not targeting this as such. Say what is it? The aerodynamic shapes and the automotive shaping, fluid dynamics, finite element machinery. So there were many fields, gene computation, and simulated annealing, different aspects as such. Right now, we are considering only two applications. They are Barnes and Ocean. So one is dealing with the galaxy evolution, another is dealing with the how ocean currents happen. So now weather prediction and weather change also is a matter of fact how that can be done. So it says that China has been able to achieve it, but at least prediction is almost globally achievable, and that's what is being done using supercomputers or the parallel computations or massive parallel processing as such. So kernels are the small piece of code with which the applications are developed. So two kernels are considered which are famous. One is FFT, so fast Fourier transform. Another is LU decomposition. LU decomposition stands for lower and upper decomposition. So that there is a factorization or decomposition with respect to given frames, with respect to the number of data points that can be considered for parallelism. So what are kernel? Kernels are small code segments whose behavior can be understood and directly track specific architectural characteristics. So whenever you imagine a say FFT, you imagine a butterfly structure. Say whenever you imagine a LU, so maybe most of the wavelet architectures you say that high high low 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 high low low. So there is some grids that can be imagined, or the architectures that can be visualized, which are structurally regular in nature. So two applications under considerations are Barnes and Ocean, as we stated. One is with respect to galaxy evolution, another one is with respect to ocean currents. So there are two separate domains of parallel computations. We'll come to that whenever I come. Just showcase the theme as such, and I feel that is more than sufficient. Even though we are not able to understand the exact mathematics involved into that particular as such. If somebody is interested, then there is a scope for parallel computation. So YouTube has a tutorial with respect to implementation of this, Barnes or Ocean algorithms onto OpenMP platform. OpenMP, where the parallel processing platform is exploited using the MPI or the message passing interface. Most of the communication that happens to the message passing over OpenMP kind of platforms. So that can be simulated, and the computation time can be with respect to the problem statement as well as the with respect to the number of processes. So whenever we are arguing with respect to that or looking in the further information in this particular textbook, so the two prominent laws that has to be in the backend of your mind is one is Amdahl's law and second one is Gustafson's law. So Amdahl's law states about bottles or sequential bottleneck. So how much is really parallelizable. So then the Gustafson's law says that whenever you invest in resources, the problem statement also should be scaled up or scaled down. So scaling of a problem statement is with respect to the Gustafson's law. So we'll look into those aspects. What if the n increases, number of computation points or the computation load increases, or what if the number of processors increase? So what happens is if number of processor increase, the processing load on every processor definitely gets reduced. But in turn, there is a communication overhead that increases, and communication prediction of a communication overhead by itself is very complex because it depends on a particular application. How what are the messages that are exchanged between the processor to compute or accomplish a particular task as such. Okay, fine. So FFT application, okay, one-dimensional version of a parallel algorithm, complex number of FT. So whenever you visualize FFT is matrix multiplication kind of stuff. Now you convert it. So there's a transposition and okay, convert to single dimension and then accomplish a particular task. So that again boils down to second or third chapters blocking of the code, so that what you invest in cache or the you have to exploit the temporal and spatial locality of the arrays or the structures whatever you want to manipulate. So they should be readily available in the cache, so that that fine grain or coarse grain whatever you are deciding, so all the contents of the how you are implementing that FFT, that core part. So the data elements required for that should be readily available. uh, then big O notations are the whenever your computation say sequential execution time n data points is n log n. So normally it is represented by big O notation. O of n is equal to n log n in this particular FFT case. What do I mean by that is, as you increase the problem statement or the problem statement gets scaled up. So in this case, if I increase the number of points or n point DFT, so n is a load for me. If I go on increasing n, my problem statement or the complexity of the problem statement goes on increasing to the larger extent. How many computations are required for accomplishing that particular task? So maybe for FFTs, some multiplications and some additions do happen, and they take some amount of time. So there is a polynomial that can represent with respect to the number of additions and subtractions, and how the time is related to the amount of computation time as such. Once you are able to predict it, so it is NP complete as such. If it may be exponential, it may be linearly scaling up with respect to the whatever the number of problem statements or number of nodes you are incorporating. So there is some graph you obtain and some expression for that. So that is bigger notation states that as you scale up the problem statement, how the computation times scales up or scales down. So some relation with respect to that. The in this case, in algorithm is a higher radix equal to root n that minimizes the communication. So that one approach where you can minimize the communication. So one is big O notation is for observing the number of computations, and root n is for observing the number of communication overhead that happens with respect to the increase in the problem statements. So, so both are increasing. Higher radix means more points or more n as the measurement shown in this appendix. Again, there is a tabular column with respect to this FFT kernel, then LU decomposition, then Barnes, that galaxy evolution, and the one more was ocean currents. So with these four applications or approaches which can exploit parallelism, so some big or the complexity versus number of processes to the communication overhead are compared. That is what is tabulated. We'll look that in further. Right now, while he explaining these problem statements, he has considered million point FFT, or the 1 million point input as such. Three primary data structures. One is input output arrays and roots of unity matrix. That is whatever the matrix. You have to have some transformation matrix so that you multiply that and you get the results. That is roots of unity matrix. Pre-computed and only read during execution. So that you know the transformation matrix. That is what is meant by roots of unity matrix. While computing, so you have to read it and multiply it. So if you are writing a C program, or how the arrays are depicted, normally they are depicted as square matrices. So that is good for user representation, and but in reality, how they are accessed in the memory is they are accessed as array elements as such. For that matter, the entire elements are stored as a single array, even though the representation may look like scattered elements as such. So 2 cross 2 or two-dimensional approaches, but in reality, in the memory, they are stored as a single array, or one after another. So he has identified 6 steps. How does the computation happens? So you transpose the matrix, then you perform a one-dimensional FFT. So whenever you are stating this one-dimensional FFT, so what is important is to perform that there are certain set of data elements and certain elements of from the transform matrix. So again, that is also one dimension, but you are not fetching continuously whenever I am moving across rows and columns. So that may not be continuous. So that you have to identify the particular block, exploiting the temporal and the spatial locality of that particular array, form that, and if they are repetitive, use them. So maybe you want to store them into a, what is that, cache. So there were an examples previously that stated the alteration with respect to the manipulation of for loops. So that inner loops and outer loops, whenever you are making that, make sure that by managing that loop indexes, you retain the repetitively required elements into the cache. So that has to be kept in mind while you are doing that, because invariably memory fetching also is important in parallel computation. Because how do you make sure that the parallel computation happens is basically depend upon how do you share the data. So whether you are going for the shared memory architecture, or you are going for MPR, message passing interface, so with which the communication overhead may increase or decrease, or so what is the amount of private memory and public memory that is available, that alters the computation time as well. 6 steps again, invariably you have to note it down. Nothing as transpose DFT, multiply the roots of, so computation happens, then transport, again perform 1 DFT, each row of matrix, transpose the matrix. The data matrices and root matrices are partitioned among processors in contiguous chunks. So you have to identify blocks and assign them to particular processor. So imagine processor in terms of a grids. So that's where the terminology grid computing comes into picture. So you have identified the problem statements, divide the problem statement to possible parallel executions, and make sure that the data elements required for the possible uh, parallel execution are readily available into the cache. That arrangement has to be made once it is done. So one local memory, whenever he is stating that, that is it is cached as such. The first row of the roots of unit matrix is accessed heavily by all the processor and is often replicated. So you have a copy in all private memories. So if you go for shared memory architectures, instead of storing into the cache, if I want to fetch it from the RAM or the some other memories, so most oftenly you may spend more time. Even it is a duplication you want to perform. So because it's a repetitive used, more often used, so whatever is that criteria, that is basically you are utilizing a temporal locality stuff, then store it in a cache. So good locality. The only communication is in the transpose phases, which require all-to-all communication of large amounts of data. So that whenever you want to transpose, so rows are converted to columns and columns. Now you want entire matrix at once. So whenever you are computing, maybe the rows into columns, or the how do I compute a first element of a matrix as it, first row multiplied by first column elements, and maybe some additions happen, and finally I'm able to compute the first element as such. So I may not store all the matrix elements during that phase. So first row, first column. So first row of first matrix, first column of second matrix may be sufficient for me to compute the first element of that matrix. But whenever you say transpose, invariably suddenly the scenario changes. Now you have to have all the elements of the what is it, from blocking to a larger block or the massive block or matrix, while you are transposing, that scenario arises. Contiguous subcolumns in the row assigned to the processor, grouped into blocks. So every processor transfers one block locally and sends the block to the each of the other processors. So some kind of managerial stuff has to come into picture, even in transpose. If it can be divided and some local manipulation, and finally something can be combined globally to produce a, or integrated globally to produce a transpose matrix as such, that can be done. So he's not specific about how it is done, but grid alignment assignment, yes, there is a possibility, and we just accept at that level as such. Spatial locality, as we have stated, is basically how do you block the elements together and make them or accessible. So similar to that, there is one more kernel that is discussed or repeatedly used in signal processing or any other parallel computation arena, is LU kernel. So lower and upper kernel. So it factors dense matrix into many dense linear algebra computations. So QR factorization, Joklowski, and eigenvalue methods. So that's where the LU kernel is being used. Again, with respect to big notation of the computation overhead, or the how does computation scale up or scale down is for a matrix S. So normally we are considering a square matrix, n cross n matrix. The running time of the big notation is n cube. So there are n cube computations required, or the computation scales as n cube with respect to the problem statement, and the parallelism is proportional to n square. The dense ALU factorizations can be performed efficiently by blocking algorithms. So n square is, so he is formulating the grid for computations, and hence it is he is treating as a n square. Somewhere he again goes back for rearrangement of the loops. So second chapter, and highly efficient cache behavior and low communication, so that whatever you require is readily available in the cache, and hence you can go ahead with respect to computation. The block size chosen to be small enough. So again, there is an optimum block size which has to be decided, again with respect to the problem statement as such. If it is small, then cache miss rate is low, large enough to and reduce the time spent in less parallel parts of the computation. If it is large, then caching becomes difficult. Then there can be many cache misses that can happen over there. Okay. So how do you arrange across the grid? Or block size is chosen to be small enough to keep the cache bit rate low, and large enough, so how to choose the optimum rate to reduce the time spent in the less parallel parts. So you have more data, normally feels that you have more computation. That's how the large or small is treated with respect to grids as such. Two details are important for parallel computation across grids. Matrix are assigned to the processor using 2D tiling. So n by n. So n is your matrix size, b is your block size, how much you are fetching. So in this case, 512 or 32, he is stating that particular block size as such. Uh, P cross P is the number of processors element that are made available over the matrix blocks. So one is block size, another is a problem statement. The third one is the processor matrix. Dense matrix multiplication is performed by the processor that owns destination block. So if somebody is able to write the final results, or he is the one who is a manager, so he is able to fork and join the things. Um, what is important in this kind of architecture is a regular structured architecture. So if whenever you imagine a VLS architecture, so that the adders and the multipliers when it's small shut that does regularity and structure is more important, so that there's a scalability aspect as well as the monitoring of the element of yeah, okay. The predictable the output is more predictable. um, okay, 1 minute. So are allocated continuously by using a 4D array with the first two dimensions specifying block number and 2D grid of the blocks. Overall, it boils down to again one more algorithm or computation theory or computational engineering is a separate branch which deals with respect to how do you make sure that you allocate a specific problem statement or the specific chunk of problem to number of processors. So why you have chosen 512 or 16 cross 16? We right now I don't have any answers for that. So he's just giving an example from the case study as such. But manual decisions, how he arrived at a particular numbers with respect to LU or FFT or Barnes applications, they are not specified as such. He's just giving a fair idea how cluster computing or the parallel computing or parallel processing happens. So BANS is a application. So N-board algorithm solving problem galaxy evolutions, how the stars or planets have evolved and how they die out of the whatever the so S. Chandrasekhar's theory of it's like birth and death of stars and further galaxies happen or happened over the period is simulated, and for which you really require N-board algorithm or the some parallel computation machinery as such. Before I go into this application, because if you imagine how the problem statement looks like, that will be fair enough, and hence I will share some of the videos and we'll discuss further. Is there an audio or not? So this is galaxy simulation. Somewhere in the mid, there is a black hole where all the different stars move on. So basically, star is born and star moves to a black hole, and finally, after a particular aspect, we'll just stop this and sorry, can go with respect to this, but it's a lengthier. I'm just searching for some smaller stuff as such. So 1,000 particles. That's fair enough, I think. So particles across the different grids and the grid sizes are varying with respect to the details available. So something similar to our wavelet algorithm. So wherever there are more details or edges, then I will have a finer grids. So wherever there are minimum details or no details, I will go with the coarse grids. So problem statement or analysis of that particular stuff is happening with respect to a lesser number of processors. So grid manipulation happens dynamically. One example, so previously whatever we have showcased was simulated with respect to CUDA environment or the compute unified data architecture. So that is CUDA or the parallel processing environment or the GPU platforms developed by the NVIDIA as such. So I will come back. Okay, sorry. So if I go with the initial stuff, MPA. So some
As a team of two astronomers, we chose to look at the problem. As a team of two astronomers, we chose to look at the problem of n-body simulations using Barnes et al. Trees and MPI. The n-body problem comes up in astrophysics because gravity is the main governing force of the universe. If you have n-bodies interacting through gravity, every single object interacts with every other object. This means that the number of computations scales rapidly. Astrophysical simulations have to tackle the n-body problem. How can we reduce the computational load?
In 1986, Josh Barnes and Pete Hutt created an algorithm that reduces the number of computations from order n squared to order n log n. The main idea is that force calculations don't need to be exact for particles that are far away from each other. We want to group far-field particles together and approximate them by their center of mass. To this end, a tree is used to represent hierarchical subdivision of space. Let's look at a 2D example. So we have this box with 23 particles in it. The root of the tree represents the entire box. The first level of the tree corresponds to dividing the box into 4 quadrants, represented on the right by 4 branches. In 3 dimensions, you would instead have octants, hence the name octatree. Each quadrant has multiple particles, so we can keep building the tree. Let's focus on the quadrant highlighted here and subdivide it further. Now 2 of the new branches are empty, and another contains a single particle, but the top right quadrant needs to be divided further until each particle has a cell to itself. In this case, 4 levels are needed to subdivide the space fully. But how do this hierarchy and tree representation help us to approximate the force calculation?
Let's look at the particle highlighted in red here and try to calculate how much force it feels from the rest of the particle distribution. The way to go about this is to work our way down the tree on the right-hand side. At the first level, 3 of the cells are located far enough from our particle that we can approximate their content by the center of mass. At the next level, the highlighted cell is not far enough away to do that, so we account for the closest particle individually while the 2 more distant particles can be approximated by their center of mass. And we're done! We've accounted for all the particles in the distribution by doing only 5 calculations in total instead of 22.
But enough theory. How do we actually implement this in MPI? We do both the tree construction and force computation in parallel. For the tree construction, we have each process construct a local part of the tree, and then we gather the branches. For the force computation, each process walks the entire tree to compute the force on the particles that it has been assigned. Let's look at some results.
We simulate 500 million years of a cluster containing 100 stars. The initial conditions follow a realistic density profile for stellar clusters called a Plummer sphere. Energy is conserved to 2%, and we get a speedup of 7 on 16 processors. Thank you for watching.
okay. Okay, then I'll just finish that. So once you have seen the video, and now I can just fairly explain that. Uh, uh, Attraction or the repulsion forces or the gravity forces with respect to any two objects, how they interact and whether how they move around or the trajectory of the movement of stars, and finally um, what is the shape of a particular galaxy and how it will be in future. So that's what they want to simulate, or the evolution of the galaxies as such. So whenever that is happening, so basically you are computing with respect to say one element under considerations, and all the remaining stars exert force onto that. So whether you may be attracting it towards it, or you may be repelling the others. Otherwise, gravity is more about attractions as such. So larger mass attracts the smaller mass, and finally, and they are moving towards apart, unlike okay, charges. There is a chance of repulsion. So normally the attraction forces is directly proportional to, I don't know the exact formula of the constants of gravity as such, but a rougher idea is masses are the product of masses is considered. So m and small m and capital M, or the whatever the m1 and m2, if you say consider that. So attraction force is directly related to their masses and inversely related to the square of the distances among between them. So that creates a fair enough idea. So if I'm considering only one star and there are 1 million which may be exerting some force onto them, and how do you want to showcase that what is my next position in whatever the time scale you want to compute that. So that brings out the problem statement. For every star, you have to predict a star's movement. All remaining stars force exertion. So whenever you are making that problem statement, so he is making some assumptions for that matter. You fix up some threshold, say that there's a bunch of stars which are very much far away from the star under considerations, and I need not compute say the force from every star because it's already very much weaker because of that distance. The force exerted is already 1 by d square ಅಂತ ಹೇಳ್ತಿದ್ರಿ. So it is squaring. So as move farther and farther, and the force exerted by it goes on becoming weaker and weaker. From that perspective, what they consider is now that bunch of stars by themselves can be considered as a individual stars. So that graining or that can be considered as one star. Maybe yes, anybody wants to say something? Okay. So center of mass of that stars, or the center point or the centroid of the that bunch of stars is predicted, and they combine together are taken as a single star, and the computation comes or computation size becomes smaller for that matter. So there is some kind of approximation is incorporated, and that's where you go with a LU kind of decomposition, so that the grids can be finer or smaller. Otherwise you have to compute for every star as stated in that particular MPI algorithm. That's where you go for some approximation, four stops of with the distance. That is what is he conveying over there. Okay, ಆದ್ಮೇಲೆ ಏನ್ ಮಾಡ್ತಾರೆ? So algorithm is n log n running time with a parallel proportional to n. So parallelism proportional to n. So that means how many how much parallelism is needed, or the n here it is stating the problem's complexity. Parallelism happens with respect to p, or the number of processors that are involved with respect to that. So Pansat algorithm uses octatree. For every node, you put up 8 children, a collection of bodies in the subtree rooted at the node. That's whatever we have seen until I reach a particular node cell. So density of space varies. So whenever you looked into that particular grid computation, or you divided the space into different blocks as such, some were having more stars, some were having only one star. So you go until you reach one star, but most of the times it is very distantly located. Then with respect to the forces that can be exerted, you start neglecting. So then you compute the error. If at all required, if the error is more above some threshold value, then you start incorporating or even going sub division of that particular space, whatever you approximated. Okay. Okay. So the center of mass is not far enough away. Cell must be opened. That means you have to go till the individual levels. This force calculations phase dominates execution time. So appendix 16K bodies. That is for this example. Whatever he is described in the appendix, he has considered as 16 kilo bodies. So 16,000 elements for computation as such. Distribution of bodies is non-uniform. Again, as we have seen across the grids or in the particular video example as such, that ununiformly distributed, and they are into motion. So changes over the time. System evolves slowly. that gives some kind of freedom for our assumption, because star movements may be in terms of 1 million, 3 million, 10 billion kind of stuff. Whenever star moves, as well as it is changing with respect to different phases as well. That is not the scope of this discussion as such, but still, nebula, white dwarf, or red giant, then black hole, or pulsar star, and so on. Um, Even those computations and how do they happen, what is the helium mass or hydrogen mass that has, again there is a scope for parallel computation. I just wanted to address that issue as such, rather than, so subtrees also vary, that is not informative. Similar to this, one more application which states how the eddy and boundary currents of a large ocean floor, the ocean currents are directed. Simulation of that is stated. I think I will share one more video and then I will come to this aspect as well. Eddy current. So, one minute, please.
Actually, and if we in the ocean.
Okay, I think this is.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder, It also has a higher concentration of salt because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them. What about the creatures that adapted to survive in these swirling seas? Take a closer look at some truly fascinating ocean dwellers with these two animations.
Okay, this was one, and
Good grammar and spelling are important, but if you want to write essays that inspire, messages that for
uh, just to showcase the problem statement or the depth that is required to handle that. Uh, One more will show one thing at the further. So I'll just have to. So I have no intention to show this completely. It's maybe 1 hour video lectures. So he's explaining or the mathematical models built with respect to that ocean currents and how they are modeled and simulated across the parallel computation arena. Uh, so you can just search it, or I will share the even the videos for that matter. So that gives a just fair enough idea, or the you can have a okay. Some scope, or if you are selecting some topics with respect to parallel computing, or I want to explore OpenMP, I don't have a good enough problem statements. What should I do whenever I say I have 8 core or multi-core kind of processors? So you can just have a comparison with respect to one or the smallest portion of these algorithms as such that can be done or predicted as such. So apart from this, again we come back to our normal textbook scenario, whatever he wants to showcase. So he's showcasing the same applications exactly, but the thing is, so red, black, Gauss ideal or multi-grid algorithm. So how you are dividing the problem statements. So the Gauss ideal marking of schemes or the assigning the computation to particular nodes is what is used in this particular application. So each update point based to previous values and the adjacent neighbors. So finite difference equations and using a hierarchical grids. So that means top nodes will compute lesser, and the lower nodes will compute more. Final grid increases accuracy, but a rate of convergence while um, they require more execution times. So final grid means grid is a small number of processes. Uh, so larger grid enhances the computation capability as such. The estimate of error at every step is used to decide whether to stay in the same grid or move on to the coarser grid. So even in the evolution of galaxies, we have seen that with that error, the same approach is being used even over here. And for this simulation, he has taken 130 cross 130 grid points and 5 steps for time iteration. So in every iteration, he alters the grid or the grid elements. That is one of the crucial aspect what has to be pointed out whenever you are discussing ocean application for that aspect. So then Overall idea with respect to parallel processing or boils down to this equation. So whenever you are targeting parallel processing or massive parallel processing, communication is a burden or a larger overhead. So if you are computing more, you will be very much happier because you have infrastructure for parallel processing or the more nodes are there. But they have to exchange some information in between, and there is more exchange that is happening between the processors rather than the computation. Then you are blocked down by the communication overhead, because the communication with respect to that problem statement may be a very complex problem by itself. Who is communicating with whom, and what he is communicating, how much is the data size, uh, what is the bus architecture whether you are using, so is it happening through NOC, whatever the, so it adds to the complexity of that parallel computation as such. Uh, so how do we evaluate that particular ratio, communication to or computation to communication overhead? So we either increase the processors, so then see that how much is really we are spending in how much time we are really spending onto the computation and how much we are spending into the communication, or you just go on increasing the problem statement, so the size of problem increase n. So as we add processor for this application, the amount of computation per processor falls proportionately. If I assume that there is a scope for parallelism, definitely that should happen. And the amount of communication per processor falls more slowly, because that communication is a complex instrument. So the information exchange should happen. And uh, he is not giving any exact expression for the big O notation. So how many times the competition is increasing or decreasing, at least at this juncture. But there is a table with respect to FFT, LU, and ocean and buns in the figure 1.1, where he is stating that. Okay. So whenever you are considering FFT, if you increase the number of processors, so computation scales down, or the per processor computation scales down. So if you increase the p ಏನಾಗ್ತದೆ, so one is increase in the n. So you can just note from the definition, p is the increase in the processor count, n is the increase in the data set size. So scaling is on per processor basis. So whatever the tabulation is made is with respect to per processor basis. Whenever you look into these problem statements, these are more complex in nature compared to the earlier expressions as such. So root of n log n divided by root of p Barnes evolution as such. With this, what we can conclude is big O notation of the identification may not be as easy as possible. So an example for that, and finally he gives a conclusion. I just leave it for you to read the problem statement. Whenever you're free, I will just close it, because we change the problem statement, because whenever you are changing the problem statement and again discussing what happens with respect to the earlier number of processors, so you are either changing the problem statement or you are changing the platforms, in the sense the number of processors that are available to take up the problem. That may not be fair enough in comparison. That's what is concluded even after Amdas law and these formulations or whatever he has computed. He has just substituted the values over there, and this is where he has suddenly jumped into grouping or clustering of four processor, and then with respect to 32, how much is the improvement that happens with respect to Amdas law. So if it is happening in that section, and with respect to communication, if I'm spending 20% in communication for this T4, so with a group of four processors, what would happen with respect to 32 processors? So you are spending somewhere around 85% of time in communication itself. Only somewhere around 15% is left for the computation, which is not good enough. And hence, that leads to a decisive factor. How many processors? So again, you have to boil down to that bell curve. Initially, whenever you increase a particular parameter, say maybe number of processors, so maybe the computation or the performance goes on increasing after some optimum number of processors. Then even if you increase the number of processors, the performance, rather than becoming improvement, it starts degrading, and hence I say it's a bell curve approach, or there is an optimum number of processor or with respect to a particular problem statement as such. So that finishes one topic, and still you have to take up the synchronization with scalability. That will take up in the next class. Thank you. Any doubts, please post it on the class message.